Hello friends, welcome to my lecture on Kuratowski's theorem. We have seen that a graph or a multigraph is planar if it can be drawn in a plane so that its edges do not cross. Kuratowski gave a theorem which characterizes non-planar graphs. A graph is non-planar if and only if it contains a subgraph homomorphic to K33 or K5. We have also seen that K33 and K5 are non-planar graphs. Now, so in a way this theorem otherwise can also be interpreted as a graph is planar if and only if it has no subgraph which is homomorphic to K33 and or K5. So, Kuratowski gave a characterization of planar graphs. Now, let us see some examples on this Kuratowski's theorem. Let us look at this example. Here we have a graph, this graph we have 6 vertices here A, B, C, D, E, F, okay, and they are joined by these edges. Now, this graph has a subgraph which is isomorphic to K33. Let us see that that means we want to show that this graph is non-planar graph. Okay. If we can show that this graph has a subgroup which is homomorphic to K33 or K5, then it will be a non-planar graph by the theorem of Kuratowski. Okay. So, let us see how we can do that. We remove the edge CF. Okay. Let us remove the edge CF. Okay. Let us remove the edge CF from this graph. By removing vertices or edges from a graph, we can arrive at a subgraph. We have earlier seen that. So, when we remove the edge CF, okay, and arrange E and F as F and E, okay, redraw the graph, then what do we notice? The graph comes in this form. Okay. So, let us remove the edge CF, this edge we remove, and transpose E and F, okay, and transpose the E and F. Okay. So, E vertex now comes here and F vertex now is here, okay, and then we see that A, which is joined to E, okay, is joined to E like this. Okay. So, this is AE, and then A is joined to B, this is joined to B here, then A is joined to D, this is A joined to D, and C is joined to B, C is joined to B here, C is joined to E, okay, this is CE. So, we have CE here, okay, and then C is joined to D, okay, and then F, okay, F is joined to D, F is joined to D. So, this is F is joined to D here, and then F is joined to E. So, this is F is joined to E, and then F is joined to B, okay, this one F is joined to B, okay. So, F is joined to B. So, the 6 vertices A, B, C, D have been partitioned into two sets A, C, F and B, D, E, okay, and each vertex of the one set ACF is joined to every other vertex of the other set B, D, E. Okay. So, this graph is K33. Okay. This graph is isomorphic to K33. Okay. So, the given graph, okay, this given graph has a subgroup, okay, the given graph has a subgraph which is isomorphic to K33, okay, and therefore, the given graph has a subgraph which is homomorphic to K33, because by the theorem, by Kuratowski's theorem, it follows that since this graph is isomorphic to K33, okay, we have K33 is a non-planar graph, okay, K33 is a non-planar graph, and so it contains a subgraph which is homomorphic to K33 or K5. Okay. So, it is this graph is non-planar, K33 is non-planar. So, we have a subgraph which is homomorphic to K33, and therefore, this graph, okay, this graph had a subgraph which is isomorphic to K33, and K33 has a subgraph which is which is homomorphic to K33. So, this graph has a subgraph which is homomorphic to K33, and therefore, this graph is non-planar, the given graph. We can remove the edge CF and transpose the vertices E and F and arrive at this graph, okay, which is isomorphic to K33, okay, and then use Kuratowski's theorem to obtain a subgroup of subgraph of K33 which is homomorphic to K33, and therefore, the given graph has a subgraph which is homomorphic to K33. Now, let us look at this one, second one. The graph shown in this figure has a subgraph, okay, homomorphic to K5. Identify the subgraph. So, what we do here, let us remove the vertex H, the edges FH and HG. Okay. So, let us remove the vertex H. Okay. When we remove the vertex H, the edges FH and GH will also be removed. Okay. Then edges FH and GH are also removed. Okay, and then remove this edge CA. Okay, remove edge CA, also remove AC. Okay, this AC. Okay, then transpose A and D. Okay, transpose A and D and C and E. Okay, when we transpose A and D, transpose A and D. Okay, you see D goes to the position of A and A goes to the position of D. You can see here. Okay, so transpose A and D and C and E. Okay, we arrive at this subgraph. Okay, this is a subgraph. Okay, which is because it is has been obtained by deleting removing the vertex H, thereby removing the edges FH and GH, and also the edge AC. Okay. So, this is a subgraph of this given graph. B is a subgraph of A. Okay. Moreover, it is homomorphic to K5, because in K5 we have this graph. K5 is this graph. Okay, this K5. So, we are adding two vertices A here and C here. Okay. When we add the vertices A and C on the edge BF and BG, okay, the graph that we get, that graph is homomorphic to this graph. So, in K5, okay, we add the vertices A and C to arrive at this graph. Okay, and we know that K5 is a non-planar graph. Okay. So, this graph is a subgroup of this graph. This graph is a subgraph of this graph. Okay, and moreover, this is homomorphic to K5, and therefore, the given graph A has a subgraph which is homomorphic to K5, and so the given graph is non-planar. The graph in A is, this graph is non-planar graph. Okay, the graph shown in the figure below has a subgraph homomorphic to K33. Let us identify that. Okay. So, what we do in this, we delete we remove the edges BD, remove edges BD, DF, okay, and CE and EG. Okay. and then redraw this graph. Okay. After removing the edges BD, this one BD and DF, CE and EG. Okay. Let us redraw this graph. When we redraw this graph, it becomes like this. You see, BC can be written as can be drawn as BC and then the vertex A here. Okay. Then this FHG can be drawn like this FH and then HG over this edge FG we put this vertex H. So, FHG we can draw like this, and then once we remove BD, DF and C and EG, okay, the graph takes this form. Now, this graph is homeomorphic to K33. Okay. So, because why it is homomorphic to K33? Because in the K33 graph this A vertex and H vertex are not there. Okay. The remaining graph is isomorphic to K33. So, this graph has been obtained from the graph which is isomorphic to K33 by adding vertices A and H, and therefore, this is homeomorphic to K33. This is graph is homeomorphic to K33. So, the given graph has a subgraph which is homomorphic to K33, and therefore, this graph is non-planar. Okay. Now, let us look at this graph. The graph shown in the figure below has a subgraph isomorphic to K5. Okay. So, what we do here, let us remove the vertex A, and then the edges AB and AC will also be AB, AC and AD will be removed. Okay. So, let us remove the vertex A. Okay. Then the edges AB, AD and AC will also be removed. Okay. And then let us redraw the graph. We bring this vertex D above this edge BC. Okay. So, we bring the vertex D above the edge BC. Okay, this edge above this edge BC, and redraw the graph. We see that we arrive at the we redraw the graph, we get the graph B, and we know that because here every vertex is connected to every other vertex. Okay, then therefore, this graph is isomorphic to K5. This is isomorphic to but K5 is a non-planar graph. So, the given graph is also non-planar. This is also non-planar. Okay. Now, let us use Kuratowski's theorem to show that the graph below given below is non-planar. Okay. What we do is, let us remove the edges joining B1 to B6. Okay. Let us remove the edges. Let us remove the edges joining B1 to B6 and B2 to B5. Okay. So, we remove this edge, okay, and also the edge joining B2 to B5, okay, and we arrive at this subgraph. Okay. We have removed B1 the edge joining B1 to B6, okay, this edge, and we have also removed the edge joining B2 to B5. Okay. So, we have B1 to B3, B3 to B4, we have B1 to B6. B1 to B6 we have removed, okay, and we have also removed B2 to B5. Now, what we do? We merge the two edges, these two edges. There are two edges at B6. Okay. Let us merge. The two edges, edges in series. At B6. Okay. We have these two edges, this edge and this edge, they are in series at B6. So, let us merge these two edges which are in series at B6, we arrive at this graph. So, B5, we have B1, B2 here, B4, okay, B3, B1 to B3, and then B3 to B4, okay, B7, okay, and we have this. So, we have this graph. Okay. When we merge the two edges, this one and this one, which are in series at B6, okay, we arrive at this graph. Okay. B1, B2, B4, B5, B7, B1, B3, and yeah, this one. Okay. And so, what we notice is that now this can be redrawn. Let us redraw this graph. We have the following. We have B1, B4, B7, okay, B2, B3, B5. Okay. So, we have B1, B2, and then we have B1, B3, and then we have B1, B5, okay, like this. Then B4, B2, okay, B4, B3, B4, B5, and this B2, B7, okay, B7, B3, and B7, B5. You can see here we have B7, B7 is joined to B5, okay, B7 is joined to B3, B3 we have, okay, and then B7 is joined to B2, B2 that is there. So, B2 should have been there. B7 is, yeah, B7 is joined to B2. So, this one here, okay, that we left out. So, B7 is joined to B2. So, B7 is joined to B2, B7 is joined to B5, B7 is joined to B3, then B4 is joined to B3, okay, B4 is joined to B5, B4 is joined to B2, and then B1 is joined to B5, okay, B1 is joined to B3, B1 is joined to B2. Okay. So, this graph can be redrawn, and we see that this graph is isomorphic to K33. This graph is isomorphic to K33, and K33 we have seen is a non-planar graph, and therefore, the given graph is also non-planar, because it has a subgraph, okay, which this subgraph which is isomorphic to K33, and K33 is non-planar. So, this graph is non-planar. Now, let's consider travelling salesman problem. A salesman is required to visit a number of cities. What is the route he should take, if he has to start from his home city, visit each city exactly once and then return home travelling the minimum distance. Okay. So, suppose we represent cities by the vertices on a graph, okay, and roads by edges connecting the cities. The length of the road may be represented as a weight associated with the corresponding edge. Okay. Now, in graph theory, graph theoretic terminology, the travelling salesman problem is equivalent to finding a shortest Hamiltonian circuit. A Hamiltonian circuit is, or a Hamiltonian cycle is a cycle where which visits each vertex exactly once. Now, if you take a complete weighted graph, complete weighted graph of n vertices, then there exists n minus 1 factorial by 2 Hamiltonian circuits. So, if you take n vertices, okay, and we consider a complete undirected graph, complete undirected graph where n are the number of vertices in a complete undirected graph with n vertices. There exist n minus 1 factorial by 2 different Hamiltonian cycles. If we consider complete directed graph, then there exists n minus 1 factorial different Hamiltonian cycles, because their direction is associated. In the case of undirected complete graph, there is no direction, so they become half, and therefore, we get n minus 1 factorial by 2 Hamiltonian cycles in the case of complete undirected graph. Okay. In the case of a complete directed graph with n vertices, there exists n minus 1 factorial Hamiltonian cycles. Okay. So, in a complete weighted graph of n vertices, of course, here we are talking about undirected graph. Okay, there exists n minus 1 factorial by 2 Hamiltonian circles. Now, one possible approach to solve the travelling salesman problem is to consider calculate the weights of all the n minus 1 factorial by 2 Hamiltonian circuits and then select the shortest one, that is but in that case what will be this problem will be very difficult to solve, because when n is large, okay, the number of Hamiltonian circuits will be too large. So, it is difficult to determine the shortest path to solve the Hamiltonian travelling salesman problem, and therefore, because of this n minus 1 factorial, even n for values of n which are not very large, okay, it is difficult to solve the consider all the Hamiltonian circuits and thereby determine the circuit, Hamiltonian circuit, along which the travelling salesman problem has a solution. So, it can be done only manually by for a small value of, for a very small value of n. Okay. For arbitrary value of n, no efficient algorithm to solve this problem is known till today. Now, the travelling salesman problem can be described as follows. This is TSP, means travelling salesman problem. It can be written as G of t, where G is the B, a complete graph. Okay, B is the set of vertices, E is the set of all edges in the complete graph. F is a function from B cross B into Z. Okay, B cross B means a ordered pair of vertices of B. Okay, so F is a function from B cross B to Z. Okay, and T belongs to Z. Okay. So, G is a graph, this T belongs to Z. G is a graph that contains a travelling salesman tour with cost that does not exceed T. Okay. So, G is a graph which contains a travelling salesman tour with cost not exceeding T. Now, let us consider this case, this example. We have consider the following set of cities, find a minimal path passing from all vertices once. So, there are cities represented by A, B, C, D, E, okay, and the weights are given to each path. Okay, to path A, B weight 2 is given, to path B, C weight 4 is given, to path C, D the weight C is given. So, let us find the path along which we get the minimum value of this minimal along which the travelling salesman problem has the solution. So, let us see, we have two paths. Okay. Because we have to consider Hamiltonian cycle. So, we have to consider each vertex exactly once, okay, while going from along this graph. Say suppose we start with A, okay, then we must consider the Hamiltonian cycle ending at A. So, let us see which path we can take. We have the path A, B, okay, C, D, okay, A, B, C, D, E and back to A. Okay, this is one path. We can also consider A, B, C, D, A, B, C, E, D. Okay, we can another possibility could be another Hamiltonian cycle is A, B, C, then we go to E, then we go to D and then we go to A. Okay. So, if we follow this path A, B, C, so then what is the total of weight? Total of weights 2, this is path 1 and this is path 2. Both these paths when we follow, we visit each vertex exactly once. So, along path 1 sum of the weights is 2 plus 4, okay, plus 3 plus 10 plus 5 and we get 2 plus 4 6, 6 plus 3 9, 9 plus 10 19 plus 5 24, okay, along path 1. And along path 2 okay, we have the total as 2 plus 4 plus and then from C to E we go, okay. So, 3 and then we go to D, okay, from E to D. So, we get 10, okay, and then from D we go to A. So, 1 2 3 no 1 2 3 4 and then we go to this 5, okay. So, 2 plus 4 plus 3 then 10, I have missed 3 here, 3, okay, A, B, B, C, C, okay, then E, D and then D, A. So, when we follow this path, how much we get? 2 plus 4 6, 6 plus 3 9, 9 plus 10 19, okay, 9 plus 10 19 plus 12, so this is 31, okay. So, here we have two Hamiltonian cycles, okay. One gives 24 value, another one gives 31 value. So, 24 is the smallest, okay. Therefore, we should follow the path 1, okay, that is A, B, C, D, E and A, okay. So, that is the solution of the that is the minimal path here, and that gives the solution of the travelling salesman problem in this case. Now, let us consider another one. Let us consider this problem here, okay. So, again we have let us start with A, Okay. So, then which path we have to take? Hamiltonian cycle. So, path 1, let us see path 1. So, path 1 could be A to B, B to C, C to D, D to E, E to F, F to H, H to G, okay, and G to A. So, we can follow this path. Another path could be again A to B, B to C, C to D, D to E, E to F, F to G, G to H, H to A. Okay. Now, let us see along path 1 what total we are getting along path 1. Sum of weights is 2 plus 1 plus 3 plus 2 plus 2. So, after D we come to E, from E we go to F, F to H. So, we have 6 here, F to H, then H to G, that so we have 5, and then G to A. So, we get 1. So, this is 2 plus 1 3 plus 3 6 plus 2 8 plus 2 10 plus 6 16 plus 5 21 plus 1 22. Okay. And along path 2 the sum is A to B. So, we have 2, then B to C we have 1, then we have C to D, so 3, and then D to E, that is 2, then E to F again 2, and then F to G we get 7, and then we have G to H, so we get 5, and then H to A, so we get 3. Okay. So, this is 2 plus 1 3 plus 3 6 plus 2 8 plus 2 10 17 22 and 3 25. Okay. So, out of these two Hamiltonian cycles, okay, the one which gives the least value is the path 1. Okay. So, we should follow path 1. So, that is the solution of this travelling salesman problem. So, the total weights of Hamiltonian circuits described in these two paths are 22 and 25. Okay. Since the total weight of Hamiltonian circuit in A is minimum, this one is minimum, the salesman should travel along to circuit in A. So, that is the end of my lecture. Thank you very much for your attention.